All right. So today we're doing the Hardy-Weinberg equations. We moved this to lab so we had more time to go through practice problems, give you more practice of actually doing the actual equations, because we're interested in determining if populations are evolving. All right. So you have the handout, you have the lab handout. We already went over all of the assumptions. What we're going to do is actually introduce the equations. All right, so Hardy-Weinberg is all based on just standard probability theory. All right, the idea is that you have a population, we have a trait of interest. That trait has two alleles, dominant and or recessive. All right, and then when our populations mate, that all of those alleles get mixed into a bag, which is effectively our gene pool. And then as we try to figure out what genotypes our offspring are, we would reach into that bag, that imaginary bag of our gene pool, and pull out two alleles. All right? If it's completely random, then the frequency of those genotypes should match what standard probability theory would predict. And we can actually do it. You can do it. It's a binomial probability distribution. I know we talk about it in the stats class a bit, but it's something that we can very easily predict. All right? Hardy and Weinberg formalized this. All right? They recognize that you have two alleles, P and Q. And these are our allele frequencies. So P is our dominant allele frequency, Q is our recessive allele frequency. And since we only have dominant and recessive alleles in our population, then the sum of those frequencies must equal 1. All right? Then, when we figure out what our offspring is, we draw two. We draw one allele from one parent, another allele from the second parent. All right? So that then gives us this equation, which represents our genotype frequency of our dominant allele, the homozygous dominant allele frequency, our heterozygous genotype frequency, and our homozygous recessive genotype frequencies. Now again, we've got three different genotypes that we have. The sum of those frequencies must equal 1. All right? So under the assumptions of Hardy-Weinberg, if we randomly draw two alleles from our population, and these are the frequencies, we should get these predicted frequencies. If we don't, then something is happening in that population. Could be just dumb luck, random genetic drift. It could be selection. It could be gene flow. All right. But what we're going to do is we're going to learn how to use these equations to make those predictions. So we're going to work through a demonstration problem. So example 1's our demonstration. We're going to use fruit flies. We're raising them up in a developmental lab. Maybe one day we'll have you work with fruit flies in another class. All right. And in our population, we have red and white-eyed flies. All right, red and white-eyed flies. And as we work through this population, we discover that the red-eyed flies are the dominant trait. So, individuals that are red-eyed could be either homozygous dominant or heterozygous. White-eyed flies have to have two recessive alleles, so they're going to be our homozygous recessive. Now, in our population, we counted 10,000 flies, which seems like a lot. So we've got 10,000 flies, and we observed 3,025 homozygous dominant red, and we observed 2,025 white-eyed flies. Now, I didn't say what the genotype is for the white-eyed flies because white's recessive, and the only way you can get that recessive trait to be exposed is if it's a homozygous recessive. What I don't give you in the problem is this. How do we figure that number out?
Homozygous recessive plus homozygous dominant, and then subtract that from the total.
Exactly. Right? We have 10,000 flies. We have 5,050 flies here, which means we have 4,950 heterozygous individuals. All right. So now our question, This is what we present. Our question is this population evolving? All right? Or is this population in Hardy-Weinberg equilibrium? So these are our observed numbers. All right? And we're going to come up with an observed frequency, genotype frequency. Our observed genotype frequency is this number, this count, 3025 over our total. All right? So this is 0.3025. A little more than 30% of our population is homozygous dominant. And we're going to do this for all of them so that we can get our observed genotype frequencies. Now, as we said, we determine if a population is evolving by comparing these observed frequencies to the predicted frequencies, assuming that the population is in Hardy-Weinberg equilibrium. So how do we make that assumption? How do we calculate those predicted frequencies? We do it using these numbers. So what we have to do is calculate P and Q. All right? So our P is our dominant allele frequency. All right, it's the frequency of our dominant alleles. I give you the equation. So what we're doing is basically counting these big R's up in our population. All right, we have 3,025 individuals that are homozygous. So each of them has 2 dominant alleles. So we're going to count those up. And then our heterozygotes have only 1 dominant allele. And then out of our 10,000 individuals, we have a total of 20,000 total alleles in our gene pool because each individual has 2 alleles. This actually works out to make a fairly easy equation that I have in the lab. All right. So if we do 2 times the number of homozygous dominant individuals plus our number of heterozygotes, 2 times 3,025 plus 4,950, and then we're going to divide it by 2 times our population size. You pull out the calculator. Should get 11,000 on the top, 20,000 on the bottom, which gives us a dominant allele frequency of 0.55. Is that what you get? Yep. Oh, that's what you get. Now, we can take a shortcut because we know P plus Q equals 1. Always. Guaranteed. 100%. All right? Math law. P plus Q equals 1. All right, we could do 1 minus P to get Q, but I always suggest calculating Q yourself. And it follows basically the same thing. This time, instead of counting up our dominant alleles, we're counting up our recessive alleles. All right, so it's 2 times our little r, plus our big R, little r's, over 2 times our population size. So I'm just going to plug in our numbers. Two times 2,025 plus 4,950 over 2 times our population size. We should get 9,000 divided by 20,000, which gives us 0.45. Now I said we could take a shortcut, but my recommendation is always to calculate P and Q, because if you screwed up one of these equations, if you screwed it up on your calculator, or maybe even wrote the wrong number down, these numbers won't add up to 1. And then you can always go back and double check. Okay, well, which one did I mess up on? All right, maybe it was here. Maybe this was the number that you didn't add up properly. Maybe you only put it as, oh, this is 5,000. And you forgot that 50. All right, So calculating both P and Q gives you a check. So now we have P plus Q equals 1. We have P and Q. Now we need to get our expected frequencies. These are our predicted frequencies. All right. So how do we get a homozygous dominant? Well, we have to reach in our gene pool and pull out 2 of these alleles. The chance of pulling out 1 allele is 55%, or 0.55. Pulling out 2 of them is 0.55 squared. So our predicted frequency is P squared, which is 0.55 squared, which gives us 0.3025. Our Q squared is the frequency of our homozygous recessive. We have our Q, 0.45. So I will do 0.45 squared. Do that on the computer, or calculator, and you get 0.2025. And then our last one is our heterozygote. So we can draw out a dominant allele first and then a recessive allele, or we can draw a recessive allele first and then a dominant allele. Both of those gives us the same genotype. So it's P times Q, but we multiply it by 2 to account for those 2 different possibilities. So it's 2 times P times Q, which is 2 times 0.55 times 0.45. And that should give us 0.4950. So the last step, compare our observed frequencies to the predicted frequencies. Do they match? Yeah, they do. Are we in Hardy-Weinberg Equilibrium? Yeah, they match. We're in Hardy-Weinberg Equilibrium. Is our population evolving? No, they're not. All of our assumptions are met. This is just random draws. Nothing's happening to our population. Now, if we rounded, we could get slightly different numbers. So if we rounded this to 0.303, you could say, well, okay, well that's different from this. No. If this gets you out to perfect 4 digits, take this to a perfect 4 digits. If this gives you a bunch of decimal points, round to 3 digits. Just go to 3 decimal places. All right? In theory, if our observed and predicted differ, even slight difference, even down to, let's say, the 1,000th place on the decimal, the population's evolved. However, I know this is a class and we're trying to make things as obvious as possible. When you get a population that really is evolving, I'm going to make sure that these things really are different. All right? Now, is there anything that we can do to check to make sure our answers are correct? Yeah, we already talked about P plus Q, right? P plus Q equals 1. Does this equal, do these 2 numbers sum to 1? Yep. All right, we're good there. These numbers are also frequencies. Those numbers will also sum to 1. If they sum to 1, that's a good thing. That's what they should. If they don't, you better go back and check your numbers. You may have done, if this equals 1, but these numbers do not, you did something wrong with these calculations. Maybe you forgot to multiply by 2. All right, maybe you forgot to multiply by 2. Maybe you used the same number for both of those. All right, but I'm going to stress now, just because these sum to 1 doesn't mean the population is in Hardy-Weinberg equilibrium. That's not how we check it. It'll always sum to 1, because all that we did is square this equation. Think back to algebra. P plus Q equals 1. If you square both sides, what do you get? P squared plus 2PQ plus Q squared equals 1. That's how you get it. All right? All right, so any questions on the demonstration? All right, practice problem 1. This is up to you to work on. All right, so we have a population of moths in England. They exhibit 2 different color morphs. Dark color is a dominant trait, while the light color is a recessive trait. In a population of 200 moths, you observe 65 homozygous dark moths and 20 heterozygous dark moths. Is our population evolving? Go ahead, take a couple minutes. I'm going to pause the video and we will come back. If I could find the pause. All right, so we have this population of moths. 65 homozygous dark, 28 heterozygous dark. We have a population size of 200. That gives us 115 light-colored moths. All right. So I already went through and did our observed frequencies. 65 divided by 200 gives us 0.325. 20 over 200 gives us 0.1. And we have 115 over 200 gives us 0.575. All right. So now what we need is our P and Q. So our allele frequency, P, our dominant allele frequency, is 2 times the number of homozygous dominants plus the number of heterozygous individuals divided by 2 times our population size. So you should get 150 over 400 or 0.375. And then as a check, I'm going to calculate our recessive allele frequency. So we've got 2 times 115 plus 20, which is our heterozygote, over 2 times our population size, which gives us 250 over 400, or 0.625. Those numbers sum to 1. Good. Looking good. Now we have to calculate our frequencies. So P squared is 0.375 squared. And when I do that, I get 0.141. This is our expected or our predicted frequency. So right now I can automatically see that something's not right. I'm not matching it. But I'm going to continue going through this because I could have easily messed up on my calculator. So take my Q squared, 0.625 squared, I get 0.391. And our last one is that 2PQ. And that gives us 0.469. Now, we compare our observed to the expected. Are they different?
Yes.
Yep. Is the population evolving? Yep. Do we know what mechanism of evolution is at work? No.
Selection.
We don't. All that we know is that we violated at least one of the assumptions of Hardy-Weinberg. So it could be genetic drift operating. It could be selection operating. It could be gene flow that's operating. It could be mutation, but, you know, the chance that you actually get a mutation where the allele flips from dominant to recessive or vice versa is going to be pretty low. All right. So now we have practice problem number 2. One more time. This one we have a copepod population. That population has long antenna and has short antenna. Long antenna is dominant. All right, so we have 300 copepods. 200 individuals have short antenna. 20 individuals have a long antenna, and that is a homozygous dominant group. So our question, is the population in Hardy-Weinberg equilibrium? Pause this and we'll pick it back up. All right, so I'm not going to work through the entire problem, but the problem gave you 200 short antenna, so we know those are our homozygous recessives. I told you we had 20. Did I say 20 or 80? 20? 20 homozygous dominant. All right, and I said we had a population of 300, so that meant we had 80 heterozygous individuals. We're going to use our equations to get our allele frequency. So our dominant allele frequency is 0.2, our recessive allele frequency is 0.8. All right, we're going to use those P's and Q's to get our P squared, 2PQ, and Q squared values. These are predicted frequencies, assuming Hardy-Weinberg equilibrium. We're going to compare them to observed frequencies. Are they different?
Yes.
Yep, they're different. So is the population in Hardy-Weinberg equilibrium? No. Is the population evolving? Yes. All right. All right, so point, notice this. These frequencies should sum to 1. They don't. They're close. It's close. What is it? I think it's 1.001. Close. It's just rounding. It's rounding for us. That's okay. All right, so when you do this, if you get like 1.001 or 0.999, it's okay. It's rounding. You probably recognize the rounding. All right, you probably recognize the rounding. So this is Hardy-Weinberg. This is what we do. Go out, population geneticists, sample populations, they get these numbers, and they see, is the population evolving? And if it is, then they go that next step and say, okay, so why is it evolving? What's the mechanism of evolution? In a lot of cases, they're focused on what's being selected. All right. All right.